So, branch cuts. So, as we'll see fairly shortly, it's only really possible to do complex analysis on parts of the complex plane where a function is smooth and well behaved. So it's therefore important to know when a function is not smooth. Now, an important example of when a function is not smooth is when a function is what's called a branch of a multi-value function. So we've just seen examples of multi-value functions like inverse functions and log, inverse trig or inverse hyperbolic functions and log. So if you recall, the reason why log is multi-valued is that when you're taking log of z, you've got e to the I times the argument, and the argument itself is multi-valued. You can have the principal, and then you can have any multiple of 2 pi added to that. So log of a complex number has an infinite number of possible values. Okay. Now, if you're doing analysis, then you don't want this choice. You just you need to choose one particular value of n and then stick with it. Now, when you do that, there'll always be a line along the complex plane where you get a jump in the value of log. This is really easiest to see if we go back just to considering the argument. We're considering log z again. It's infinitely multi-valued since n can take any integer value. But if we consider the values of log n, they're going to vary smoothly, ignoring what happens at z equals 0. Except when the line, the principal argument equals pi, in other words, the negative real line is crossed. Because then the imaginary part is suddenly going to change from, because if you go along the negative real axis, then the principal value of the argument there is pi. But if you just go slightly below the negative real axis, then suddenly you get to a value of the argument of minus pi plus a little bit. So for example, if we consider z equals -1 plus I epsilon, when epsilon is positive and very small, and then we work out what log of that will be, and then we consider z is -1 minus I epsilon, which is just below the negative real axis, then log of z with n equals 0 in our formula will change from approximately, so we've got, this is modulus approximately 1, so log of 1 is 0, but then we've got the argument. So the argument we're dealing with here is approximately, in this case, the argument is approximately pi minus epsilon. And here the argument, the principal argument, is minus pi plus epsilon. So you see the value of log z is going to suddenly jump as we cross from this point to this point, which are very close together. Log z, however, so z is barely changes. It changes by 2I epsilon as we move from this point to this point. But log z, in contrast, has a sudden jump of 2 pi I as it crosses the line, the negative real axis line, theta p equals pi. Okay, now if n is fixed, then, as you've just been talking about now, log z becomes single valued, as I mentioned, but it has a jump. But we refer to this single value function defined only in the region where theta is between minus pi and pi. So it's not actually defined when theta equals pi, but between that region, where it's smooth everywhere in that region, as long as r is greater than 0, the distance from the origin is greater than 0. We refer to that function, single value function, as a branch of the multi-value function log z. So, and in general, a branch of any multi-value function f is a single value function, big F, which is analytic, which we'll define shortly, over all of its domain, the values it can take, the input values. And at each point in its domain, f of z equals one of the values of the multi-valued function f. So, for example, the single value function principal value of log, capital log n, in that region is just one of the branches of log z, which is a multi-value function. And normally we call the branch corresponding to the principal value of a multi-value function as the principal branch. Right, so now we come on to what's called a branch cut. So there's a line of points where the branch is not defined, since that would lead to a discontinuity if it were defined that there. And this is known as a branch cut, or so a cut line or branch line. So it's basically where the function is discontinuous. So in our example, we're looking at the principal branch of log. Log z has a branch cut along theta equals pi. And similarly, any of the branches for a fixed value of n have the same branch cut. But these, and this is basically, we draw a branch cut normally as a dashed line. And the importance of branch cuts will become clearer later on when we considering integrating around, we do line integrals around the complex plane. And basically the line integral golden rule is not allowed to go through a branch cut ever. But we're not actually forced to choose the branch cut along theta equals pi. We can actually choose a branch cut to be along any angle we like. So we could choose to have the branch along a particular angle theta. We could choose to have the branch along the real axis and say that we're going to write log z in this way, where theta is allowed to vary between 0 and 2 pi. And then the branch cut would be along the real axis, the positive real axis. Or we could say that theta is allowed to vary between any particular fixed angle phi minus 2 pi and the angle phi, which is illustrated here, and then the branch cut would be along here. So basically, we can choose the branch cut to be along any angle we like. Normally, we choose case A or B is the most useful, but sometimes occasionally we choose it to be sort of along this the negative imaginary axis. It's also used sometimes. Now, we've got this free choice of branch cuts. There's going to be a point which is, if you've got a choice of branch cuts, there's always a point which stays the same independent of which branch cut you use, and that's known as a branch point. It's fairly obvious that log z has a branch point at z equals 0. This all maybe seems a little bit abstract until we come on to a bit more concrete, some more concrete examples. Now, another important multivariate function is z to the power alpha when alpha is not an integer. Now, really, this just reduces to the log z case. In fact, pretty much all branch cuts in the end reduce to what happens with log z. Now, z to the alpha in general, we've seen, is defined by this expression here, e to the alpha log z. Now, e to the z is a nice smooth function everywhere, except at z equals infinity. So that means that z to the alpha, which is e to the alpha log z, is going to have a branch cut in exactly the same place as log z. Now, if alpha is 1 over n, what happens? Well, if we work out the expression, we end up with log z, which we can write as principal part of the principal value of log of z written in polar form, z equals r e to the I theta, and here you got theta p plus 2 pi m. All of that, okay, we're dividing by n. So the mth branch, so here we've got the mth branch of log. Okay, we're taking log of z, and this is the mth branch. The mth branch of the log function actually just corresponds to the mth possible value of z to the 1 over n. We recognize this as something familiar. This is what we recognize as the formula for log of 1 over n, but we actually got it via this formula here when we're expanding log in the normal way. So when m equals n, then we're back to where we started. When m equals n, then we're just adding 2 pi again. We get exactly the same number again. So sure enough, z to the 1 over n only has n branches. So whenever you write a multi-value function like log or something raised to the alpha where alpha is not an integer, you should always associate those multi-value functions with a choice of branch, and therefore a choice of branch cut. Normally use the principal branch, which means that when you take which basically means taking the positive value of the square root. And the branch cut for these functions is normally chosen to be either along the positive real axis, theta equals 0, or the negative real axis, theta equals pi, depending on the problem. So question 10 is really intended to give you some idea about how these branches work and where the discontinuity, how the sort of discontinuity arises. This time, read the question carefully. It's along the positive axis.